Good morning. The paper I'm about to present is entitled Escada, Predicting Virtual Machine Network Bandwidth Demands for Elastic Provisioning in Infrastructure as a Service clouds. It proposes a new model to automatically characterize virtual machine network traffic and predict its future bandwidth demands. Cloud computing, and especially infrastructure as a service clouds, offers elasticity in the provisioning of computational resources of virtual machines, which enables its customers to dynamically specify the capacity to be provisioned to their resources according to its desires or requirements. A challenge faced in this context is that of determining the appropriate capacity of resources to maximize performance while minimizing costs. When the appropriate capacity is not known, one can end up under-provisioning resources, that is, provisioning lower than appropriate capacity, and as a consequence limit the performance of their applications, or one can end up over-provisioning resources, that is, provisioning higher than appropriate capacity, which results in superfluous costs, both to the customer and the cloud provider. There are three research lines related to the challenge of identifying the appropriate capacity of resources, or in our case, the appropriate bandwidth. The first line goes in the direction of diagnosing the provisioning. These works identify the current provisioning level of resources, that is, if they are under-provisioned, over-provisioned, or correctly provisioned, but do not provide estimates of the appropriate bandwidth in scenarios of under or over provisioning. Another body of work uses time series analysis to try and predict the future appropriate capacity of resources, which is important because cloud workloads are not static over time. However, the majority of these works focus on the prediction of CPU and memory, and even those that focus on network bandwidth do not address the impact that incorrect provisioning may have on the measured time series used to train the analysis. When a network interface is under-provisioned, the traffic is distorted, making transmission rate measurement inaccurate with relation to the real traffic demand. How should statistics obtained in these scenarios be analyzed? The last research line is orthogonal to our work and focuses on offering bandwidth guarantees to virtual machines of virtual infrastructures. These assume that the appropriate bandwidth of every virtual machine is known in advance, and use this information to carry out tasks such as virtual to physical infrastructure mapping. The identification of appropriate bandwidth brings opportunities both to cloud providers and customers. To providers, it enables a more informed and optimized management of the cloud infrastructure, one which is able to maximize the utilization of physical resources while meeting customer service level agreements. To customers, it enables to correctly provisioning of resources, which optimizes the trade-off between performance and costs. In this context, we present Escada, a model that focuses on network provisioning by estimating and predicting the appropriate bandwidth to provision virtual machines. The impact of provisioning levels was taken into account in its design. Thus, it addresses over and under provisioning scenarios and is able to accurately estimate and predict the appropriate bandwidth from statistics obtained from periods with any provisioning level. Continuing the presentation, we will first discuss the evaluation of Escada, showing the accuracy it achieves, and after that we will then describe its design details. Escada is composed of two parts, an estimate model and a prediction algorithm. Now we first evaluate the estimate accuracy of Escada in different levels of provisioning. To evaluate this estimate model, we run it on multiple scenarios with different levels of provisioning, starting from severe under-provisioning, where the provisioned bandwidth is only 40% of the required bandwidth by the workloads, and going through to significant over-provisioning, where the provisioned bandwidth is 160% of the required bandwidth. This experiment applied 4 workloads with different traffic characteristics. The y-axis of the graph shows the bandwidth estimated by our model as a percentage of the required bandwidth, and the x-axis indicates the provisioning level of each scenario. Each colored line refers to one of the workloads, and the black line represents the maximum network demand that can be observed by straightforward measurement of the virtual machine transmission rate, which is the method applied in related works. The transmission rate is limited by the provisioned bandwidth, thus it is not possible to measure the real traffic demand when the network is under-provisioned. We observe that our model's estimates are always better than the measurement of the virtual machine transmission rate. The greatest error of Escada was an overestimate of 25%, when the network was severely under-provisioned, with only 40% of the required bandwidth for workload 2. On the second experiment, we evaluate the prediction behavior of Escada. The graphs represent the evolution of bandwidth predictions as the workload demand varies over time. The x-axis indicates the intervals of the experiment, and the y-axis indicates the real required bandwidth, the estimate provided by their models under test, and the bandwidth that was reserved in that interval as a result of the prediction. We see that in interval 4, both the state-of-the-art model and Escada underpredict the required bandwidth, under-provisioning the virtual machine. Because the state-of-the-art estimation mechanism is not able to estimate the real demand of the traffic, the model continues under-predicting for 9 intervals. Escada, in its turn, is able to accurately estimate even in the face of under-provisioning, allowing its prediction mechanism to recover more quickly and start to provide more accurate predictions. Thus, Escada recovers from an under-prediction error 3 times faster than the state-of-the-art model. In this final result graph, we zoom out from the previous graphs, showing various cycles of the previously presented intervals. Because prediction algorithms depend on historic training data to learn the variation behavior of the workload over time, they may take a while to converge to a stable prediction state, that is, a state in which every prediction tends to fall close to the real bandwidth. Escada reaches a stable state after 14 cycles. The state-of-the-art model takes 17 cycles to converge and tends to underpredict more frequently than our model, which may limit the performance of the virtual machine applications. Our model converges 25% faster to the stable prediction state than the state-of-the-art model. With these results in mind, we will now see how does Escada is able to achieve this estimate and prediction accuracy. Our proposed model for required bandwidth estimation is inspired by multi-class queuing theory. A simple application of queuing theory is that of calculating the minimum capacity of a server to serve customers arriving at arbitrary rates and with arbitrary utilization demands. In our example, to attend to 5 customers in a minute, each with 10 required actions, a server must be able to carry out at least 50 actions per minute, so that the queue does not increase indefinitely. Our model applies a similar logic to network packet flows passing through the virtual machine network interfaces. Escada first monitors packet flows in the interfaces of a virtual machine, then after a categorization stage, it identifies the typical transmission demands of the flows using a clustering algorithm. A classification stage is used to calculate the typical arrival rate of each typical flow class, and finally the required bandwidth is estimated considering the calculated transmission demands and arrival rates. Next, we will see in further detail some of these stages. Escada starts its flow of execution with a stage of monitoring. The network interfaces of a virtual machine are monitored during a fixed period, and the packet flows observed are recorded. To each flow we record the first and last timestamp in which the flow was observed, the source and destination addresses, the communication protocol, and the number of bytes sent and received through the flow. The flow categorization stage separates flows that were observed completely, that is, from the moment they started until they ended, shown in red in the figure, from those who were only observed partially, shown in blue. As we will see in the next slides, the two categories of flow records are considered differently by the model to address the impact of under-provisioning to the measurement of traffic. The clustering and summarization stages are responsible for identifying the typical data transmission demands of the recorded flows. It applies a clustering algorithm strictly over the complete flows, as only for those that were recorded the total demands. After the clustering, the model summarizes the formed clusters or groups into representative flow classes. Each flow class has an associated transmission demand and arrival rate. At these stages, only the arrival rates of complete flows are calculated. The flow classification stage calculates the total arrival rates of the flow classes formed before. Complete flows are directly classified by the clustering algorithm, while the partial flows need special processing because they did not record the complete demands. Correctly classifying the partial flows is essential to obtaining accurate estimates, since they represent flows with demands that were not completely fulfilled, probably because of bandwidth limitation. The partial flows are classified considering three scenarios: optimist, pessimist, and intermediary, and their arrival rates of flow classes concerning partial flows are calculated using the mean between these scenarios. In the optimist scenario, every partial flow is classified to the class with the minimum typical demand among all classes with a higher demand than the recorded one. This scenario represents the minimum required bandwidth that could be required to transmit completely the partially observed flows. In the second scenario, called pessimist, every partial flow is classified to the class with the maximum typical demand among all flow classes, regardless of the recorded demand. This scenario represents a probable maximum required bandwidth that could be required to transmit completely the partially observed flows. In the third and last scenario, intermediary, we distribute fractions of each partial flow between classes with typical demands higher than the recorded. The fractions are attributed according to weights that are calculated using the number of complete flows previously classified to each class. This scenario mirrors the distribution tendency observed in the complete flows and provides a middle ground between the two previous scenarios. The last estimation stage calculates the required bandwidth using the transmission demands and arrival rates of the flow classes. The demand of each flow class is multiplied by the sum of the complete and partial flows' arrival rates, and the sum of all products results in the bandwidth estimate. This bandwidth estimate is then used to train the bandwidth prediction algorithm. The prediction algorithm applied by Escada is an adaptation of the expert tracking algorithm proposed by Lakurtz in 2014. The algorithm maintains an estimate history and a weight associated with each past estimated interval. Each past estimate acts as an expert, suggesting that the next interval will have a certain bandwidth value. Weights are updated regularly to reflect the accuracy of each past estimate interval to predict the next interval. The bandwidth is predicted as a weighted linear combination of the estimates in the history. The algorithm was previously shown to make accurate predictions when the estimate history provided to it is also accurate, which is now the case with our model that is able to accurately estimate even in the face of severe under-provisioning. In this presentation, we noted that knowing the appropriate capacity and correctly provisioning resources in infrastructure as a service clouds is crucial to maximize the utilization of the cloud infrastructure, meet service level agreements, and optimize the trade-off between performance and costs. Our proposed model, Escada, provides accurate bandwidth estimates even in scenarios of severe under-provisioning, and is able to recover from under-prediction errors 3 times faster and also converges to a stable prediction state 25% faster than a state-of-the-art model. Thank you for your attention.